What's up, YouTube? Welcome to the next episode on So You Think You Know C Sharp. It seems that a lot of people seem to have liked that video. I've had a plan to make this series for many, many years, not just weeks or months. I just didn't get down to it. And I've done a lot of this stuff also in my Programming with Intent. So for me, the So You Think You Know C Sharp series and the Programming with Intent series and the So You Want to Be a Code Reviewer are all connected. I just seem to be breaking it up in slightly different compartments. A lot of the content that was covered in the previous one and in this one has been covered in another video, but its title was different, and as a result, people may not want or may not know to go look at those videos for this kind of content. So in many ways, this is a repetition, but I'm of course going to add more content, more information, since I'm now dedicating each of these to one or two specific topics. Today's topic is static classes. Essentially, we're going to go under the hood, going to look at some of the issues or some of the benefits of statics, and then also look at implementation, if you will, at the memory allocations level and what the implications of that are to static classes. And then there'll be guidance on when to, when not to, and what to be careful of when you do use statics, what you shouldn't do. And these guidelines are mainly my own, so I might miss a few things, but I use statics a lot. But when you use statics a lot, you have to know what you're doing, because if you don't know what you're doing, then it could be pretty bad. As in the outcome of using statics can be pretty bad, hard to find bugs, issues that you can't even pin down to the fact that there's a static class somewhere that's being used or misused or not correctly programmed. So anyway, without further ado, let's get started. What's a static? We all use static classes, like the convert dot something is a static, and then of course the string class has a bunch of static methods on it, and we use those a lot. For most people, it's like, oh, so you don't need an instance of an object. And then, so when you don't need an instance of an object, you should make it a static. Yes, you don't need an instance of an object, but that doesn't mean that's the reason for making something static. So the question becomes, what are the thought processes you would use to determine, one, if something can be static or not? So it goes like this. Static classes cannot be sent as method arguments. Static classes can't be returned from methods. So if you have a need to pass something to a method as an argument or receive something from a method as a return argument, it can't be static, right? So right off the bat, that's off. Two, statics don't support polymorphism, of course. So if you need an instance in order to create something polymorphically or to have a hierarchy of classes that you intend to use polymorphically, then you can't make that class a static. The other is static classes cannot implement interfaces. Thank God for that. Yeah, static classes can't implement interfaces. So if you have the need to implement an interface, it can't be in a static class. Right? That's just how it is. So at a high level, these are the deciders, if you will. So I actually always start with, I want to make everything static. Now that might sound weird in an object-oriented programming language, but it is true. It is something I've developed over the years, and I've just found more and more that I prefer to use statics instead of instances, because for the most part, even when I have an instance, there's only one instance. So if you only have one instance of something in your entire application, why do you need an instance? Right? So in my mind, not in my mind, it's actually the way I program. There are, at a high level, two types of classes. There are classes that we use in some sort of polymorphism for behavioral change at runtime. And there are classes that are DTOs, or value objects, not value types, value objects. These are classes that have properties but no methods. In other words, they have state but no behavior. And the other kind has behavior but no state. That is classes that I have an instance for. These classes typically have behavior but no state. Right now, I explain a lot of this in my Programming with Intent videos where I talk about autonomous methods and I talk about pure virtual methods or functions from the functional programming world, the differences and the similarity between these two things. For the most part, I strive to have either pure functions or methods or autonomous functions or methods. So as a result of that, my behavioral classes, they can certainly use polymorphism in case I need that. And so there'll be multiple instances, so they won't be static. But there are many classes I have in my systems that have behavior, but they don't need polymorphic usage. There's only one instance ever, so why do I need to have an instance when all I'm doing is I have this one instance? And because they are autonomous, methods are autonomous, or methods are pure, they don't maintain state, or they have no state. The DTOs, on the other hand, like a customer DTO, well, you can have 1,000 DTOs in memory at any given moment in time, and so you do need instances because every customer has slightly different data, and you want to work with all of them simultaneously. So the DTOs will have instances. Each DTO instance will have its own state. These classes are immutable. So you have to define the state or the values at the time of creating the instance, and it can never be changed once it's been created. And you have thousands of those at runtime, and so you have the need to have instances, but these classes only have state and no behavior, and the state is immutable. As I said, so there's the two sort of families, if you will. The DTOs that are stateless, that are stateful but no behavior and are immutable, and the other classes that have behavior but no state. So they have no sort of properties, or these properties that maintain state, and they're behavioral, but they're not necessarily being used in a polymorphic sense. And there could be other classes, of course, that are polymorphic, and so they need to be instance types. So the behavior classes, for the most part, can be static because they are stateless. They have behavior, but and their methods are autonomous and or pure. So they could be stateless. They could be static. So if they could be static, then I use them as statics. Now, you have to be careful with statics, because if you make a mistake, or anybody on the team makes a mistake, there are subtle bugs that are hard to pin down and hard to even find or determine that it's happening over here because of this one class. So be very careful. But having given all these caveats, let's take a look at statics. I'm going to start with the memory representation or conceptual memory representation of objects in .NET, and then talk about statics from that point forward. So if you look over here, this is a conceptual memory representation of some object. This variable, let's say, is on the stack. So you created a new info, and this info is the variable name. This variable points to some location in memory. 4 bytes above that memory location is what they call the sync block index. Every object has a sync block index. This is mainly used for multi-threading purposes, so we won't worry about that for now. The next 4 bytes is the method table pointer, and these next 3 here are properties of this info type, where these are value types. So that's an integer, that's a double, and this is a datetime. And so they are stored inline within the object's memory allocation itself. The object also has a name property, which is a reference type, of course, is a string. And so it's got a pointer to some other location where there's another object, in this case, a string object. But every instance of an object will pretty much look like this, right? So what I wanted to get from here is when you allocate an object in C#.NET, think of it like that. Like, visualize this conceptual model. Okay, so it's not just some location. It's got all this stuff in there. Now I'm going to go deeper in here so you can then further understand the cost, if you will. Remember, my decision to use statics is not based on cost, and it's not based on any performance benefits. It's purely based on the fact that I don't need an instance. And if I don't need an instance, why the heck am I creating one? But you got to be really sure you know how to use statics. Anyway, going back to this memory representation, remember we are in a managed language, managed environment, and the C# compiler produces IL. It doesn't produce native code. Then the jitter, or the just-in-time compiler at runtime, so just in time, will compile that IL to machine code. So when you new up an object instance and you want to call a method on that object, that method has not yet been compiled. It's compiled to IL, certainly, but it's not actually been compiled to native code. It's going to be just in time compiled. So the method table pointer has a set of methods, the table, if you will, and each of these entries here is a pointer to the compiled code of that method. For example, let's say there are some methods here in this class here. Then there'll be a pointer to the method here, and the method itself will be somewhere else in memory, some other location, the compiled version of it. So every time you call this method, when you say info.so-and-so method, is going to come here, find the address location for the method, then go to that compiled address and execute the code over there. Right? So if the method has not yet been compiled, the jitter will then compile it and then populate that value for the method table here. Say this method is at this address location. Right? So I'm not showing that detail here, but that's what it is. For methods that are part of the base class, if in case this were in a hierarchy, then all base class methods are common, if you will. And so they'll go here, and from there it'll find the compiled version. If it's not been compiled yet, it'll compile it and then put the compiled version's method pointer in here. All right. Now, the bare minimum size of a .NET object instance is 12 bytes on a 32-bit machine and 24 bytes on a 64-bit machine. By bare minimum, I mean just if you just define a class and you say open, close, curly, and that's it. Nothing in that class, no properties, no method. It's 12 bytes. Now, 12 bytes may not sound like a whole lot, but in a larger system, that amounts to quite a bit. Now, in .NET, we also have a type of type. A type of type. 3 types. Sounds confusing and it's unfortunate, but that's what it is. The type, the name of the type, like object, is type. So we have a type of type. Just like we have a type of type object, we have a type of type in .NET. And the reason this exists, and I'm going to give you a mental model to think about as a way of, for you to remember it, right? Think of the class that we write in C# in our code here as the kind of the information we are giving to the runtime. Saying, hey, I would like a class like that. It kind of looks like this. It's got these methods, it's got these properties, and so on. The runtime has to make sense out of that thing that we envision and the way we describe it. It has to take that thing and it has to convert it into something it understands. So it takes our class definition, like the C# class definition, and it converts that to something it understands. Now, when you want to new up an instance of your class, or you want to call a method on this class, or even if it's a static, you want to call a method on a static method on the class, the runtime has to understand what it is that you're doing in the first place. So it has to take your class definition and it says, you know what, and for me to understand this, I need an instance of this thing in memory somewhere so I can work on it. And that thing is the type instance. So just like we have a type, this is the type instance. In C++, when I was doing C++, I was learning by myself, but I used to think, why do they call this a class object? Because the object is an instance of a class. So why keep saying class object? Why not just say object? Like now in C#, we just say object. We don't say class object. But in C++, they say class object. And the reason is that in C# we also have a type object. Well, sorry, I didn't mean that they're calling it in C#. In C++, they also have this notion of a type object. But now in C#, not now, we've had this notion in C# since the very, very beginning called a type object. So what is a type object? It's the instance of a type. So going back to what I was saying about the runtime, in order to try to make sense of your class definition, it has to convert it into something it understands. And that what that is that type. And then once it has that type, it has to create an instance of the type before it can do anything with your type. So the moment you say new so-and-so type because you intend to call set a property on it or call a method on the class, the runtime has to create an instance of the type object. So just like an instance of a class is an object or class object in C++, an instance of a type is a type object. Make sense? All right. So looking back at the diagram I have here, this instance has in the method table, it has a type object pointer. So that's again just a pointer to the actual memory location in which there's the type instance. So this type instance is an instance of a type, and it looks very much like an instance of a class in terms of this, the memory allocation and the structure that fans out from there. Like, if the method has not been jitted, it's going to be jitted first, and the method table will hold a pointer to that jitted method, the code there. It's like it repeats itself. The type instance here is pretty much another thing like this, but this thing is just pointing to that first point here. So this is the same or synonymous to that from a type instance standpoint, and this type instance looks very much like the instance here, right? So every instance of a type has a type object pointer that is nothing but pointer to the type instance that type is come from, if you will. Now in .NET, we are guaranteed that there will always ever be only one instance of a type per app domain. One instance of the type per app domain. Now, what is an app domain? For those of you who may be a bit confused about what the heck is an app domain, it's kind of like a Win32 process, but imagine you've compiled a console application and there's an exe now on the file system, and you double click that exe and you run it. So you have one instance of that application running. That one instance is running in an app domain instance. If you double click the exe again and another instance runs, that's a separate app domain, right? So each app domain is guaranteed to have exactly one type instance. So one instance of a given type. All types that you're using, that you touch in your code, will have a type instance in the app domain, but there'll be exactly one. So that's like a guarantee you get from the .NET runtime that there will ever only be one type instance per type in a single app domain. Now we can use that to our benefit. I'll talk about that a bit later. But just try and conceptualize this. If I have an instance of an info over here, and in order for it to exist, the type instance has to have existed. So that's the type instance here. And this type object pointer points to that instance. What happens when I create a new instance of an info object, another instance? So of course, that'll be somewhere else in memory. And it would also have a type object pointer. Where is it pointing? Exactly, it's pointing to the same type instance pointer. So all object instances are pointing to the same type instance in the app domain. Now in VB, they have a really nice name for it. I'm not a big fan of the name itself, but it explains exactly what it is. They call it shared. So what we call static in C# is called shared in VB. And shared is, in some ways, what's happening here. So it's a valid name. Not that I'm saying I would prefer C# to have called it shared. It's just that it conveys the message better. So the type instance or the type object is shared by all class objects of the same type, right? So they all point to the same location, and they all share that code. If there are static methods in that type instance, they're all there and they'll all share that code. Right? So there's only one instance of all those methods in memory. No matter how many threads are operating on it, there's just that one instance. Right? But you can't have you can't have a class instance. You can't have a class object to static classes anyways. You can only have type instances, and you can only have one instance of the type. I hope that's clear. I'm going to move on and we'll talk about some other things now. So if there's only one type instance and everything is shared, in other words, if there's a static method, it's going to reside here as part of just like here, there's a method table pointer, there's a method table pointer here, and the method table pointer points to a table of methods. And for each entry in the method table, there's a pointer to the actual JITted code, if you will, or the address of that JITted code. And it's all there. It's just like another class object. It's a type object. So, and the guarantee that you have only one instance in the app domain, which is really important because you can take advantage of that quite a bit. All right. So what are the guidances for if you've already decided that you can have this class to be a static, given all the previous conditions, that is, if you don't intend to send this instance as a method argument or get it returned to you from a method as a method return type, if you have no need to implement an interface, if you have no need for polymorphism, your thing could probably be a static class. Unless you said, okay, then therefore it should be static, right? You have no need for polymorphism and so on and so forth. So you now start to implement your static class. What are the guidances for when you do that? all methods must be autonomous and or pure. Right? All methods must be autonomous and or pure. Now, I'll briefly go over what autonomous methods are and what pure methods are, but make sure that all methods must be autonomous and or pure. The class should have no state, no properties. If those properties exist, they don't ever change. So the class could maintain state, but it's unchanging state. It's sort of not necessarily immutable. It's constant. Like it doesn't change. So it can maintain state. It may be a need for some properties, some constants. Just make sure they don't ever change at runtime. And all methods and methods. So what is a pure method or what is a autonomous method? I'll talk about the autonomous methods first. This is my term, by the way, autonomous method. I used to use it before I discovered functional programming where they use pure, but they've pure methods in functional programming have a slightly stronger sort of meaning to that. And I'll give you the difference. Autonomous methods are methods that operate only on the information that has been provided to them as part of their method signature. They don't rely on state. Now, without trying to confuse you, that's not to say it can't rely on properties. Those properties that themselves are, let's say, stateless, right? You have a constant string defined somewhere. Of course, that method can use it because that's not never changing. So you can have properties that don't ever change. But essentially, this method, if it's autonomous or for it to be autonomous, it can only operate on the arguments that are given to it as part of its method signature and nothing else. If you can build methods like that, design methods like that, and you should, that method in my world, in my vocabulary, is called an autonomous method. Now, the difference between autonomous methods and pure methods are those where, from a functional standpoint, methods are pure if they don't change state. Now, I'll make the distinction. Let's say in my static method, I'm updating a database, or I'm sending off an email, or I'm writing to a file in the file system. All of these things are considered changing state. The state of the world has changed in some form or fashion. That is not a pure function. So a pure function will not do that. A pure function is just like an autonomous method, except it's pure as in it will not allow or will not make any changes to state. An autonomous method is free to make changes to state, but is not operating on anything else except for the method, the arguments that came in this method signature, right? So when you design a static class, make sure the methods are autonomous and or pure. And this does not maintain state. These two things are just paramount, key to being safe while using static methods, static classes, I mean, all right? What can go wrong with static classes? A lot. Besides the multi-threading issues that you might have. Now, you won't have multi-threading issues if you're not maintaining state and if all your methods are autonomous, right? There's no notion or no potential. I mean, there could be, because what you're getting themselves could be modified by multiple threads at the same time. Let's say I get an instance of a DTO that's not immutable, and I'm mutating it in my autonomous method. I have no clues that there's another thread that's mutating the same instance, which is why my DTOs are always immutable. That gives me that guarantee. Just to give you guys a sense, I would say, and I'm not done a count necessarily, but I would say at least 50% of my classes are static in my systems. At least. There could be others that are static, and for some reason I don't make them static. I can't necessarily explain it to myself or to you. I just know there's an instance, there's only one instance of some of these classes, and I have no real need for the instance because these classes are essentially autonomous and or pure methods. So they don't maintain state. They have behavior, but all the methods are autonomous and or pure. So I could make them static. I just can't tell you why I don't. But there are many, many other classes that are static, actually static. And they have been static for many, many years. Again, the same principles apply, guidelines apply. No state and autonomous and or pure methods. Right? And you can be fairly confident. And if you're using DTOs or if you're passing DTOs to these methods as arguments, the DTOs need to be immutable. All right? Because you may have an issue with multiple threads. Not you may, you will have issues. All right. So the problem with statics, other than the multi-threading issue I just talked about, is more to do with design or implementation where once you have a static class, it kind of becomes a dumping ground for all kinds of things. And now you can't make sense out of what is this static class for. It's got everything. It's got the utility class, right? So I would stay away from making utility classes to the extent, first of all, they should not be called utility. Right away, that's going to be a red flag for me. If you call something a helper or a utility, it's going to tell me you're not thinking hard enough. If you name your things, your static classes or any classes correctly, they'll be fine-tuned to be less general and more specific. And when you have more specific class names, those classes are doing something that's very specific, and the methods that they contain are cohesive, as in they're grouped correctly to do what that class says it's doing. It's not a utility for everything, right? You don't want that sort of thing. So stay away from defining classes that are utility classes, and also static classes should also be internal. I wish I could make them private. I wish you can make them private if they were like nested classes. But for the most part, static classes are not to be shared across your system boundaries. Right? They need to be confined within your system. You're using them for your dedicated purposes. These classes are so deep in the guts of the system that they're doing very specialized work. If they're doing specialized work, you shouldn't be sharing them on the outside, right? So for the most part, static classes are internal. There are cases or times when I have a static class that's public to be shared by the outside because it's the functionality it provides is fairly complex. It's very specific, but also fairly complex. And rather than somebody having to repeat the same implementation, I make it public so some other assembly or project can use that static. So I think I've covered, hopefully, all the gotchas, guidelines, do's and don'ts, and how statics actually work. I've also got to see one more thing I got to talk about. The singleton. I'll probably make a separate separate video on the singleton design pattern, but I will use this idea that there can only be one type instance per app domain. That's what you use or make use of when you define singletons. And along with that are member initializers. That it's either like when you define a member variable in a class and you initialize it at the time of declaring it, those play a significant role in singletons, as well as they have certain ideas or concepts behind them that will be important. So I'll probably cover that in a separate video. So for this video, I'm going to keep it as just statics. So I hope this has been a useful video. I hope you learned a thing or two and were surprised by some things. Did I confuse you? I hope so. Well, this was not going to be confusing. It was just more like an eye-opener. So I hope your eyes have been opened. And I appreciate any comments and likes and notifications. Please hit the notify button because then you will get notified each time I upload a new video. And thank you for watching, and I will see you next time.